We're going to look at central angles and their arcs, and then we'll be looking at inscribed angles and their arcs. But before we talk about this, we need to know what is a central angle and what is an inscribed angle. So notice that a central angle, its name kind of gives it away. The vertex of the angle is at the center of the circle. So you'll see that the angle is centered at the center of the circle, and then it subtends or it opens up to an arc. And the degree measure of this angle is the same as the degree measure of the arc that it opens up to or it intercepts. So if this angle was 45 degrees, the arc measure would also be 45 degrees. So central angles have the same measure as the arc that they intercept. Let's think about this in another way. So here we have the same situation. There's your angle that is at A, that's 45 degrees, and the arc that subtends it, or that it subtends is 45 as well. However, what if I wanted to know the measure of the associated major arc? So remember minor arcs from our vocab that we looked at. Minor arcs are named with only 2 letters because they're less than 180 degrees. We don't need to use 3 letters. We just need to use the 2 that arc is between. So here's BC, that's a minor arc. But there's another major arc, and when we're naming major arcs, which are any arcs larger than 180 degrees, you need to use 3 letters. And that degree measure of that arc is going to be the remainder of the 360 degrees of the circle, right? We've got 45 degrees here. We have the 45 degree angle measure that was here at angle A. Well, what's remaining is whatever's left. Remember, there's 360 degrees total in a circle. So take away the 45 that's taken up by angle A and by arc BC, and you'll get 315 degrees. That angle measure is 315 degrees. Therefore, the arc measure from B around to C in the other direction, so we'll call it BDC so that we know we're going in that order. That major arc is 315 degrees, the remainder of the 360 degrees in this circle. Now let's talk about arc length. If I want to know the length of an arc, so I want to know not the measure in degrees, but I want to know the length. Remember, an arc is a portion of the circumference of a circle. So we can easily find how much of that circumference is taken up by an arc by using just a fraction. Notice this 2 pi r here. Guys, that's the circumference formula, right? So if I want to find the arc length, all I do is I take the circumference formula and I multiply it by whatever percent, we use a decimal form, but whatever percent of the circle is taken up by that arc. So we find the angle measure, take the angle measure of the arc out of the entire 360 degrees in the circle, and this will tell us what percent of the circumference is taken up by the arc. So what we're doing here is we're taking however much the arc takes up times the circumference formula, and that's going to tell you how much of the circumference is taken up by that arc. So, for example, we have JK as our arc here. And we know that the arc measure, so notice the difference between arc measure and arc length. Arc measure is like angle measure. It's in degrees. Arc length is like a distance, a length. So the arc length is referring to the actual distance of that arc. If I know the radius is 6 millimeters, and I know that the arc measure is 60 degrees, we just plug it into this formula we just talked about for arc length. Arc length is equal to however much the arc measure is, which is 60, out of the total in the circle, which is 360. So this is telling us this is how much of the circle it's taking up, times the circumference of the circle, which is 2 pi r, when we know the radius is 6. So this ends up being, we're going to take 60 over 360, 1/6, or you can just put this into your calculator. times 2 pi times 6, we actually just end up with 2 pi, or about 6.28 if we are rounding, and that would be in millimeters. So again, if you put that in your calculator, it'll just spit that all back out for you. But that is how we would find the arc length if we're given the arc measure. We use this formula right here, so make sure you write this down, commit it to memory, have it around so you can use it. The arc length is equal to the measure of the arc angle divided by 360 and times the circumference of the entire circle. One more thing we want to talk about is inscribed angles. So if we have the vertex of the angle, instead of lying on the center of the circle like our central angles, and that's what P and M would be, or NPM would be here, sometimes we have inscribed angles where the vertex instead is actually on the circle. So you can see the angle cuts across the whole circle here. Oops. So angle SLM here is an example of an inscribed angle. You'll notice that those sides of the angle are actually chords. So it's kind of cool. The sides of the angle that are inside the circle are actually chords of the circle. They cut across the circle just like I was talking about. So both of their endpoints are on the circle. There is a theorem about inscribed angles that says that the actual angle, the inscribed angle, is half the measure of its intercepted arc. So an inscribed angle has a measure that is half of its intercepted arc. So if, for example, this arc was 126, the inscribed angle would be half of that. It would be 61 degrees. And it works vice versa. The arc is twice the length, twice the measure of the inscribed angle. So if this inscribed angle was, say, 42 degrees, oh, it doesn't want to work, 42 degrees, and the inscribed angle was 42 degrees, then the arc would be twice that, which is 84. So they have that special relationship, whereas the central angle is equal to the arc measure. This one, the inscribed angle is half. So make sure you have that noted and you remember that as you go forward.